Okay? Okay, so if you've got a pendulum and X is your displacement from equilibrium, you're going to have a force this way. You're going to have a net force in this direction. Now, if you're holding it, of course, your net force is 0, but if you release it, then you're going to have a net force in that direction. So if it's freely swinging at its position X, it's going to experience a net force of negative Kx. And we can prove that using a little trigonometry, but I'm not going to do that. Okay? Just some similar triangles and a little concept of force. Okay? So this is net force on a free pendulum. So, and if you, on the surface of the Earth, the net force, the K would be negative mg over L, where m is the mass, g is the acceleration of gravity, and L is the length of the pendulum. Don't have to worry about that, I just mentioned it. Newton's second law says that the net force is mass times acceleration. Acceleration is the second derivative of position, as we should know from calculus. Okay? Velocity is the first derivative, acceleration is the rate at which velocity changes, that's the second derivative of the position. This equation is easily rearranged. That's right. To this. Okay? So how do you solve it? That's all there is to it. Okay? Now, if I do a non-homogeneous thing over here, like cosine of t over here, okay? Or some multiple cosine of t, some function, force function, that has a period of 2 pi, okay? Or cosine of 7t. Period would be 2 pi over 7, pre-calculus. Okay, and of course you want to understand all the stuff you learn in second semester pre-calculus about sine and cosine functions, their period, amplitude, frequency, etc. You got to know those things, okay? Because they're going to be applicable to the examples, real-world examples. I'm just giving you one real-world example, okay? So you can use the techniques we have here to solve this equation. And if you have something else over here, that means you got some kind of driving force on this pendulum. Or it's a kid in a swing and you're pushing it with a certain frequency. That's all there is to it. You have a function over here that gives you the push. And you got a little drag in here, okay? So you might have an x prime term because the drag could be proportional to how fast you're moving, if it's air drag, okay? If it's the flexing of the chain and rusty hinges, gets a little more complicated.
Kids dragging their feet on the ground.
Sorry?
Kids dragging their feet on the ground.
Yeah, well, you know, that's, yeah. And that's, well, we model that force, but it gets complicated, and the differential equation gives you some guidance if you assume a constant force dragging the feet on the ground, okay? But then as the kid gets a little higher, the force reduces, and it gets very complicated. And you get a pretty complicated differential equation you never solve, except approximately, okay? We can still understand the behavior by looking at that differential equation and making approximations. Okay, so anyhow, you got this, right? So that's one typical real-world example, and it's really kind of foundational for a lot of physics, because that's where you get simple harmonic motion. Okay? And, yeah, we'll do some of that in detail, probably next time. But I'll probably ask you a couple of questions about that equation and a couple of conceptual questions, just to get used to thinking about forces and acceleration and mass. Okay? Make sense? Okay, good. Okay, well, we'll go on from there.